So last time, if you remember, we discussed Engel's theorem, and there was a tiny thing which we had to do. Let me remind to you what we have there. First of all, the theorem. It says that if you have a representation rho of an nilpotent Lie algebra in some space, and this is true for complex number of complex field, real field, actually any field of characteristic 0. If you have a representation, then it is possible to find a basis in V, such that for every element in G, the matrix of the corresponding transformation will be a strictly upper triangle, zeros on diagonal, zeros below diagonal, and something above diagonal. Actually, I even don't try it, because what we really need is the following lemma, which is called also Engel's theorem in some books. There exists a vector V in V which is annihilated by any element of Lie algebra. I prefer to use, today it will be important, this short notation for the action of the algebra. I don't write a row of Xi, I write just Xi. Xv is 0. The main ingredient of the proof, this is inductive proof which uses the induction with respect to the dimension of OG. And the main ingredient is the following fact, so sublemma. This lemma follows from Engel's theorem, so it may be regarded as part of it, that for a nilpotent Lie algebra there exists an ideal of codimension 1. And it will also be nilpotent, also has representation in V, so we can apply induction and so on. But this is the main thing. We need to construct this ideal. And I want to say that I wasn't able to do it last time because my time was over. But actually it is not difficult. This sublemma is proved in, how to say, a stronger statement, very slightly. It proves the following. Suppose that we have any subalgebra. Then there exists another subalgebra, C in G, between B and G, dimension of C is dimension B plus 1, and B is an ideal in C. So we can take any subalgebra, extend it very slightly, and get a slightly bigger subalgebra, such that this B will be an ideal in dimension 1. Certainly, it is more than we need, because as soon as we have this, we can apply this fact several times to get our sublemma. How to take any subalgebra. If you cannot think of anything else, take 0. Take some subalgebra B say 0 in G. Then according to this, there exists a C1 of dimension 1, where 0 is an ideal, not too much. Then there exists a C2 where of dimension 2, such that C1 is the ideal dimension 1, and so on. We do the do, and then we reach the happy end. Cm will be simply G. And this is an ideal dimension 1. Okay? Now, so this is what we need. And this is done in the following way. We consider the space, so you remember, we have B and we want to construct C, right? We consider the quotient vector space. It's not an ideal, so no structure. And this is a B modular. B acts in it. So there is a representation of B in I didn't say. Maybe I should say it now. Induction is induction. I suppose that for every dimension less than dimension of G, the fact is true. I mean the angle theorem. So we can apply the angle theorem to this representation. And since the dimension of B is less than the dimension of G, there exists a vector W in G B, which is annihilated by B. So at W is 0 for every at in B. W belongs to the quotient. We can take the representative in G. W is not 0. I didn't say this. Actually, it was also important to say there, otherwise take 0 is okay. So it's not 0. And then when we take its representative, it is not doesn't belong to B, right? Because it is not 0 in the quotient. And just we take B plus the ground field, whatever it is, right, K. So we did I know C times W tilde, where C is an arbitrary constant. So just extend B by this W tilde. And that's all. Because certainly it is a subalgebra and B is an ideal there. It is checked in 1 second. So if you take eta plus CW and some element in B, zeta, take the commutator, it is the representative of is the adjoint representation. And this will be this plus this. And this certainly means that this belongs to B. So everything belongs to B, and we are done. Okay? No problems. So this sublemma, we have it. And now how to deduce the main lemma in angles theorem, the angle theorem. From this, it is also very simple. Maybe I can do it here. We take G, we take H, in ideal dimension 1. We take NXC in maybe GT in G minus H. Right? Also, for H, the theorem is correct. So there are vectors in V. In V. We consider the same representation in V, only restricted to H. So there exists a vector in V, vector in V which is annihilated by H. Not one vector. So there exists a subspace W in V, which is annihilated by, and this is non-zero. Non-zero vector, so that means that the space of all vectors which are annihilated by H is not zero. We have now, again, variables like this. Zeta is not in H, but still, I know I have to use more space. So I continue that. Still, I want to say that W is zeta invariant. That is, zeta W belongs to W for every W in W. Belongs to W means what? Means that it's annihilated by B. So take eta by H, take eta in H, and write eta zeta W. You want it to be 0, but it is zeta eta W plus eta zeta W. This is 0 and this is 0 because eta and also this commutator belong to W. So this is 0. So W is a vector space with a representation of H. And we can apply the theorem, Engels theorem, and get W is a space where it's Z with the operator zeta. And this operator certainly is nilpotent because all comes from the representation. So by the theorem, there exists, no, not by theorem. Not by theorem, just operator must have kernel. So we don't need any theorem here. So there exists a W0 in W, which is annihilated by zeta, simply because zeta is an important operator in the vector space, non-zero vector space W. So this is not equal to 0. And this W is what we need. It is annihilated by zeta and by H, so it is annihilated by G. And everything is done. This is the which I was not able to consider last time. Questions? Remarks? Yes?
So up here, your first W, you got that, you know that exists through induction?
There I use the induction, yes. And here I don't need any induction, simply nilpotent operator. Okay. Yes. Induction not with respect to this lemma, induction with the whole theorem, with the whole theorem. Yes. So we have this statement, I mean Engels' theorem and all its corollaries. In particular, we discussed it last time, every nilpotent Lie algebra has non-trivial center. In particular, every nilpotent Lie algebra has ideals of all possible dimensions. Well, we have dimension 1 next, we can, but it follows from the classical statement of Engels' theorem that there are ideals of all dimensions. Maybe something else, but I don't remember. So if you don't have questions, yes, you have a question.
Okay, so this is going way back to the beginning, but so B is just a subalgebra, right?
Yes.
Yeah, so what do we mean by G over B and the representation?
The space. A vector space in a subspace. Okay. You can take the quotient. This is not a Lie algebra, but representation in a space.
Okay.
Yes. If you really don't like it, you can take 0 for B, and 0, believe me, is an ideal. And then everything will be okay. But no, still C1 will not be an ideal in G. So we need this sublemma for a subalgebra. Subalgebra, and C is not also a subalgebra, not an ideal, but it contains B as an ideal. And then we make this sequence of extensions. More questions? You? You, George? Colin? Paige? Who else? Now, if we are done with nilpotent algebra, the next thing also,
Just to
yes.
continue on Dale's, G mod V is just going to be the largest subalgebra where D has a faithful representation.
G1, what's G1?
G mod B, G quotient B.
G quotient B is the quotient space.
Yes.
In what sense is it largest?
Well, if you take a right, there's you're quotienting by the things that B acts on trivial.
B acts, well, trivial or not, it is actually the whole representation may be, whole the algebra can be commutative. So trivial, let it be trivial. Nilpotent, what is important for us?
Sure. Yes.
Yes. Yes. Now the next thing. If we are done with nilpotent Lie algebra, the next class to consider is the class of solvable Lie algebras. Actually, certainly, the Lie theory mostly exists for classical Lie groups and for simple and semi-simple Lie algebras. But first, we need to consider such things which can be regarded as ugly, although they are not. So, a solvable, do you know the meaning of the word solvable? I prefer the following meaning. There are two ways how to explain this. G is a Lie algebra over some field. Well, I can say characteristic 0 simply that you don't ask anything, but in this definition it's absolutely the same. G prime. This Agner notation means the commutator subalgebra. So the subspace of G spanned by all possible commutators of elements of G, and this is a subalgebra, this is an ideal. The quotient is commutative. And we can so the algebras are less and less, and G is solvable if this chain is finite. So at some step we get 0. This is one of possible definitions of a solvable Lie algebra. Another one which you can easily guess, a chain of ideals in G. So G contains H1, contains G1, G2, G3, and every G is an ideal in the previous G, not the whole G. With all the quotients commutative. You may know the word solvable group, I don't know. The same meaning in algebra. Solvable, I don't know what. Module. Solvable Lie algebra. I said the field is arbitrary, but in reality, the main result will be obtained over an algebraically closed field, which we can denote as C. So C is field of complex numbers, or if you are on the algebraic side, say that it is algebraically closed field of characteristic 0, will be okay. But I will consider complex numbers. I will call elements of this field complex numbers. By the way, from this definition, it is clear, very clear, that G solvable algebra does contain ideals of all dimensions. Because if you have any space between these two, it will be G prime is an ideal in G, so any space between them will be an ideal in G. And so on. So all spaces between these spaces are ideals in In G, actually, it is also not hard to understand. I will use the fact that G has an ideal of dimension 1 without any future explanations, but it is so. Now, the theorem of angle says that an nilpotent Lie algebra over any field, actually, of characteristic 0, can be represented by any representation, any nilpotent representation, can be represented by strictly upper triangular matrices. Matrices which have zero diagonal and also zero below diagonal. For solvable algebras, we have the same, only we should delete the word strictly. The fact is, but this fact is true only over complex numbers, that if we have an arbitrary representation of G in V, and G is solvable algebra, then there exists a basis so that every operator in V, which is determined by an element of G, has a matrix of this shape. Not strictly, simply upper triangular matrix. This is what the Lie theorem says. It's immediately clear that we need to have this fact that the field is algebraically closed. Not even for Lie algebras, that's for operators. Or if you prefer to speak of Lie algebras, consider the very much one-dimensional Lie algebra. Then its representation is the same as just linear operator. And a linear operator in a real space cannot be reduced to this form because lambdas are eigenvalues of this operator, and if they're not real, then no hope. In the complex case, yes, at least one operator can. So if the Lie algebra G has dimension 1, then it is obviously true, just fact from linear algebra. And this can be regarded as the beginning of an induction. But again, instead of this theorem, I will prove another theorem. Lemma, which again I want to repeat all I said about Engel's theorem, which again in some books is called the Lie theorem because it is obviously equivalent to the Lie theorem. So lemma, which I'm actually going to prove. Suppose we have the same as before. That is a solvable Lie algebra representation. Then, so we have these things. Solvable Lie algebra representation. Over complex numbers, everything. Then there exists a vector V in V and a linear map lambda from G into C in functional on G, so that for every Xc in G, Xc applied to V is just lambda of Xc times V. So V is a simultaneous eigenvector. Again, V is not zero. V is a simultaneous eigenvector for all operators in provided by G. Eigenvalues are different. Obviously, have to be different. Just multiply an element of G by 2, and your eigenvalue will be also multiplied by 2. Eigenvalues do depend on the element of Xc. Oh, maybe 0. Lambda may be 0. I didn't say anything else. But I want to say that there exists a linear function on G with this property. There is some terminology in classical theory representation which can be applied to this. I prefer not to insist on it now because in the classical case it will be sort of have slightly different flavor. But still you can say that for the functional lambda there exists a word weight, which is right. And if lambda is a weight for representation, then there exists, so lambda is a weight, and there exists a non-zero space V lambda, which consists of all V and V, such that again for all C and G, C V for all of V is equal to lambda of C times V. The word weight is right in some sense, although the notation G is wrong in this context. Because now we will apply it to solvable algebras. Then we will actually consider mainly the case when G is nilpotent or even commutative. Not G, it will be subalgebra or some other. So it will look different. But the definition, but if you want to call it the weight space, it is very much wrong. Because weight space actually in classical representation theory is defined in a different way. Now we can use any terminology we wish to use. But notation V lambda is okay. Also, we will have another notion similar to this. But lambda will be rather a superscript than a subscript. So it will not contradict too much to my notation now. Good. So forget about all this. Forget, please, the word weight. I even can erase it. And the statement of my lemma means simply that there exists a weight, what I have just erased. So there exists a functional lambda, say that for at least for some non-zero vector v, the equality written on the board now holds. So how to prove that? First impression that it's very easy. We consider, oh, I didn't say, you need to say this, that certainly this lemma is equivalent, well, it follows from the Lie theorem, but also implies it. Because if you have some representation, then you find this vector. And we find this lambda, and this space be lambda. And the space be lambda certainly is a sub-representation, because every element of C operates in it as multiplication, so at least preserves it. We factorize V over V lambda and consider and apply the same result to the quotient, which also will be representation of the same algebra. And then we move and we get what we want. Now, when you try to prove this result, then the first impression is that it is very easy. And then you discover that one boring thing actually requires a proof. And moreover, when you try to prove it, the first impression is that this cannot be right. So, how to prove it if you sort of ready to believe? We consider an H. So, induction, yes, induction. We use induction. We use induction. So for Lie algebras with dimension less than dimension of G is okay. Dimension 1, it is okay. Dimension 0 is more, even more okay. So we take ideal H in G of dimension 1. Later I will G is eta plus C zeta with eta in H, C in C, and zeta is some fixed element. So any fixed element in the difference between G and H. I have my representation of G, then it is also representation of H, and hence, according to my induction hypothesis, I have what? I have a functional, I denote it by mu, not to confuse with lambda. And I have, I prefer to write, oh, mu, W mu. This is the space. I should W, that's okay. The space of all V in V such that eta of V is mu of eta V for every eta in H. Okay. Then I make a statement which seems natural. Actually, W is a subspace of V. And in V we have a representation of G. And I make the following statement. That W is invariant with respect to this representation. That is zeta. So remember, zeta is an element in G minus H. Zeta W is contained in W. As soon as you say that probably it's correct, I immediately finish the proof of the lemma. Why not? It is a very convincing proof of anything. So suppose this is correct, that zeta takes W into W. Why not? As soon as it is true, zeta becomes a linear operator in W. A complex vector space, a linear operator, that is the eigenvector. So there exists a W0 in W, so that zeta W0 is equal to some number, let me denote it as eta times W. Obviously so, eigenvector, any linear operator has an eigenvector. Then I define lambda of eta plus C zeta as mu of eta plus C times nu, or you can say simply that I define lambda on eta on H as restriction of as mu. And on zeta it will be this number eta. And then it doesn't require any effort to prove that yes, if you apply this, if you say C is equal to eta plus C zeta, and you apply C to W0, then you get the lambda of C W0. Well, all we know about W0 is in W, so this holds for every eta, and this holds. So together they give this result. The proof is over. The only thing, but I said this to you, if, I don't know, maybe you will agree that if I say that it is obvious, very much obvious, that W is invariant with respect to any element of G, you probably will be willing to believe, and then it will be all. But let me be, this time, let me be honest. So let us try to prove it. So actually, this is correct, but requires a proof. And at the first moment, it seems that it's impossible. At the second moment, it is clear that this is correct. Let me do that. So I hope that you follow me, that you that we have this W. You remember the definition is now on the board. Because it's zeta not in H. Now let us try to prove, only try, that for a W in W, for a W small and W large, we have zeta W. I want to prove it's also believed to W. What does it mean? This means that if you apply eta, eta is an arbitrary element of H, to this, then we want to get, let me write what? Lambda, mu, yes. Mu of eta, this is W, and this will be okay. But let us look what happens in reality. This is equal to zeta eta W plus the commutator, eta and zeta, applied to W. This is this, because eta W is mu of eta times W, and zeta is linear operator. So but this is equal to mu. This element belongs to H, because H is an ideal. And at this moment, it seems that it is a disaster, because we have a term which precisely makes the difference between what we want and what we have. The only hope, if it can be called a hope, that by some mysterious reason, or not mysterious, it is zero. And it happens to be so. So now I want to prove that actually this is zero. Moreover, actually this result has nothing to do with many things which we have. What is G? G is solvable Lie algebra. I don't need it anymore. Lie algebra. H is a Katamenes of an ideal. I don't need it anymore. It is an ideal. And then we have a weight vector. Representation, yes, as before, of G. On H, we have a weight, mu, a weight space, and so on. So, suppose that we have now, what written here? So W is in W, which means, as you remember, well, we can write it, that eta W is mu of eta W, right? We have C in G, in general not in H, but I don't mind. It was zeta, now I don't see because it is absolutely arbitrary. And now let me do something very simple. Take this W. Take CW. By the way, we even do not know that this is an element of W capital. Still, this is some vector. Apply C once more. Apply more. And we stop at the moment when the next vector will be linear combination of the previous ones. So vectors, they are linearly independent, at some moment, well, infinite sequence, finite dimensional vector space. So at some moment there will be a vector which is linear combination of those. Then I stop. Now I consider this space. And denote it somehow, say Z. And I want to do the following statement. Can I read this? I prefer to stay at this board. I want to say that any eta, an arbitrary eta in H, first preserves this space. You understand? It is not done from the very beginning. So there arises a map. And this map, in the basis, which will be, this is a basis, right? And this map has the matrix mu of eta. The diagonal consists of numbers equal to mu of eta, zeros here and something here. This statement is not too hard to prove. And it will give us all we want. What do you think where I should begin? From gives what we want or from the proof? Both are very simple, so the order is arbitrary. Let's begin with proving this. So from the beginning, it is even not given that eta preserves the space. W, yes, but not this and all the rest. From the beginning, it's not clear. But I say that eta does preserves the space W. It's a subspace of B. Preserves, so W is invariant with respect to eta, and moreover, the matrix in this basis has the shape. Another statement is that this is very much obvious. A formal proof using induction and long formula is given in my notes, but who cares about formal proofs? Apply eta to these vectors. Eta applied to W is mu of eta times W. So this first column is okay. Right? Eta applied to this is this times mu of 0, nothing else. What is eta applied to Xi W? Well, as we already had somewhere, it is Xi eta W, right? Plus eta Xi W. But this is what? The first term, this is this, apply Xi, so the first term will be mu of eta Xi W, and the second term will be mu of eta Xi W. Because this is an element of H. What about that? I don't see what, if you are going to have objections, I don't precisely see what you are going to say. Precisely what we have here. So second column, mu of eta here, and something which we do not specify here. It is specified there. Instead of doing formal induction, let me make a computation for the next term. Eta applied to C squared W. It is Xi eta Xi W. So one of these Xi I switch with eta plus eta Xi W, right? This, well, we know this thing, it is written here. So this is mu of n, mu of eta, Xi squared W. Xi W comes from here, and one more Xi. Plus from this, mu of eta Xi, Xi W. Xi comes here. Then this, again, the same. CW. And one more term, you remember. So when we apply this to CW, then according to the same formula, we'll have something times W. This something actually is mu of eta Xi. But I don't care. Again, if you look at the matrix, you see the diagonal term is okay, and two more terms which involve Xi W and W. This both give you Xi W and W. And that's all. So you can make a formal induction, and if you don't want to do it, it is written in my notes. Then you ask, I know what you ask. Ask, what of that? And here I answer. This is done for eta, but let us do the same. Let us do the same for the commutator. Eta c, eta what? Eta zeta, whatever. I don't see it anymore. Zeta, whatever. Eta c, well, let's say eta c. It is an element of H, because H is an ideal. So still we have this. And the matrix of this is what? According to this, it will be mu of eta c, mu of eta c, something here, and 0 here. Simply apply my result to this. And then the last word. Would you mind to pronounce it? What about this operator is a commutator of two operators in W. What do you think, say me frankly, of traces of commutators? Yes. So the trace of this is 0. But if the trace of this is 0, then mu of eta c or whatever is 0, which completes the proof. Well, still you need to invent something to prove this. Because you should pass through a very dangerous point. At some moment we see a formula which shows that what you want to prove is not correct. And somehow you need to survive at this moment. After it, everything is obvious. Well, so this completes the proof of Lie theorem. We will apply it many times. And in the remaining, I don't see precisely how many, 3 minutes or something, I just some more things related to nilpotent and solvable algebras. First, no, not for nilpotent solvable algebras. Suppose that we have a very arbitrary representation, complex or real, of some Lie algebra, absolutely arbitrary. Now I want to look at my notes, just not to consider the set of all ideals n in G. I didn't say that these ideals are nilpotent. I denote them by n. Set of ideals say that the representation rho restricted to n is nilpotent. There are some ideals of this kind, for example, 0. Yes. The set of ideals, they may contain each other. And I state, and it is obvious, but I have only 1 minute, so I just state it, that actually there exists the biggest ideal, which contains, with this property, which contains all the rest of them. So this family of ideals has a unique maximal element. There exists an ideal with the property which contains all other ideals with this property. And it is denoted as eta sub rho. It is an nilpotent ideal. Just to make it clear, it is not right that n rho is simply the set of all elements of G which provide nilpotent operators. They do provide nilpotent operators, but it is an ideal. In particular, we can do this for the adjoint representation. And you get a nilpotent, some privileged nilpotent subalgebra of an arbitrary real algebra. And probably this is where I need to stop. This is called the nilpotent radical. We will consider this more, and also there is a radical. A radical is a solvable ideal, biggest solvable ideal in some sense. And nilpotent ideal is biggest nilpotent ideal. Both notions, especially radical, are very important in the Lie theory. So this I will consider next time. Thank you for your kind attention.